Hello everyone, welcome to another video in my channel, and in this video we are going to discuss about a very popular algorithm which is used to render graphics, which is called ray tracing. So ray tracing is a very popular algorithm used to render realistic looking three-dimensional graphics on screen, and it's extremely popular in the gaming world, not just gaming world but anywhere in any place where rendering is required. So in this video we will try to understand the basics of ray tracing, its internals, how it works, and we'll try to render one very simple scene using ray tracing from scratch. So at the end of this video we should be able to render a scene like this with a few spheres. I chose spheres because it's the easiest shape to render and it's mostly used in ray tracing 101. So yep, this is something which we are going to render from scratch. So without further delay, let's get started. Okay, so first let's have a look at our environment setup. So I'll be using C for this. So the entire ray tracer that I'll be building here will be built in C. And for drawing on screen, like drawing pixels on screen, I'll be using raylib, like I have done in my past projects. So you don't have to necessarily use raylib. Even if you choose to use any other thing, still you can follow this video. You can use any other library which allows you to draw bitmaps, or you can even render bitmaps by hand. You can write your own bitmap printer, but as of now for this video I'll be sticking to raylib because raylib provides some pretty cool functions to generate images from pixels. So I'll start with a simple raylib template. You can get this template from this repository. I have mentioned about this in one of my previous video. I'll put a link to that video in the description. This template is compatible both with Linux as well as macOS. So right now I'm on Linux. It's a very simple raylib project structure. There is a include folder which has various raylib header files. You can delete all of those. We don't accept the raylib.h and raymath.h. You can get rid of raygui.h and physec.h. I'll do it right now. Because we don't need those in this project. These two should be fine. And we also have libdarwin. This is again not required for Linux because as a prerequisite to setting up this template you need to install raylib on Ubuntu, and the instructions are mentioned here how to do that. Okay, so that's it. So let's set up a very simple raylib project which allows us to print things on screen, that is print pixels on screen. So for that I've created a main.c. So what I'll do is I'll start with including raylib.h, and that's it for includes as of now. And I'll start with defining the default FPS, which will be 60 frames per second, and then I will define my main method where I'll initialize the window. It will take a screen width and screen height and a label, and set target FPS. Okay, and we do have to define this constants as well. So let's define them, like the screen width and the screen height. Define screen width. So as of now I'll define both screen width and height as 800. And now I'll generate a blank image. So for that I'll do image equal to image color, and the width and height will be the width and height of our screen. We will give it the background color of white. So the color values take a alpha channel as well, so I'll just make it 255. The other thing that I'll do is I will create a tiny function which will allow us to draw a pixel on the image, that is a pixel on the image that we just created. Void screen draw pixel, color C, image star image, and here we will simply call image draw pixel, which allows us to draw a pixel at any position, and we will simply draw that pixel with color C, and that's it. So this might look very trivial right now, like and as well as redundant, but we will soon see why we need a separate function. We will soon make some transformations here, and that's the reason I'm defining a separate function for just printing a pixel. So another thing, after the other thing we'll be doing is we will export this image to a file, and we will call it o.png or out.png, whatever. I'll just simply call it o.png as of now, and we will return 0. That's it. So that's a pretty simple raylib project. It does nothing, but it simply has a few methods for generating an image. And also let's test it out once. We will just draw, let's say at 10,10, we will draw a pixel of color let's say red. Let's do it a few more times so that it's big enough for our eyes to catch. Okay, so we are missing the image parameter, and we'll just send a reference to image. Right, that's it, and let's just change the coordinates. So we'll make it 11, 12 and 13. So we should get a tiny dash like thing or a line. And to compile this, I've created a tiny makefile. So this makefile comes with the template itself, but I have made certain changes. So I've just made a certain customizations. So on building, it simply builds the project. On the run recipe simply runs the program, which is as usual, and the show recipe actually shows the image depending on which platform you are using a particular image viewer. So on macOS we are using Open, and on Linux, since my desktop is GNOME or GNOME, the image viewer I am using is Eye of GNOME, EOG. And yep, so the gen recipe simply runs everything and shows us the image, right? So let's try to run this. I'll do a make gen, and if you see, we have got a tiny red dash here. It's not visible that clearly, but there is a tiny red dash over here, which means our printing by pixel on the image is working, and it creates a o.png, right? Actually, it's okay to get rid of this usual stuff like the screen size and stuff. Let's try to generate once again, and we still have this image being generated even on removing the screen setup and everything, which is good. Okay, so that is our basic setup, and now we know how to generate the image on our disk. We have an easy way to open it, view it, compile it, and everything. So now let's dig into the ray tracing algorithm. So what ray tracing does at the core is it tries to paint a given three-dimensional world or a three-dimensional scene onto a two-dimensional plane, which is our computer screen, right? So that is what it tries to do. So our computer screen is intrinsically a two-dimensional plane, and we need to render the three-dimensional objects that we see around us on this thing. So how do we do that? So it's pretty much similar to how we paint a picture on a canvas, right? So let's say we are outdoors and there is a nice scenery, like there is a very beautiful landscape, and we want to print it. So we see whatever reaches our eye and we try to interpret that and we try to draw it. So let's say there is a simple landscape for now. Well, let's define our landscape. So this is what we are viewing. So let's try to draw a simple landscape. So let's say we have some mountains over here. Excuse my sloppy drawing, but it's just an example. Okay, so this is a very simple landscape, and let's say we have a canvas over here. So let's say this is our canvas, or this is the surface where we want to draw this screen, and we are the painter, right? So I'll just quickly mark this. This is the canvas. So now, how do we draw this landscape on our canvas? And let's say we don't know how to draw. So one very simple way to achieve this, or to draw this even without knowing how to paint or anything, is we come up with a net-like structure through which we can see, and that net has got a grid made on top of that. So you can consider it as a tiny window through which you are looking at the landscape, right? And that window has got certain grids. So let's kind of define our net that I'm trying to mention. So let's say this is the net-like structure, or this is the window which has got grids. So let's define a few grids. How many lines are those? 1, 2, 3, 4, 5, 6. So it's 6 rows, and let's make it 6 columns as well. 1, 2, 3, 4, 5, 6, right? So what we are now doing, we have placed this net-like structure, or this window of grids, in front of our eyes, and through this net we are trying to look at the landscape. So one clever trick that we will apply is we'll divide our canvas as well into this grid of 6 rows and 6 columns. So let's do that. Now it does not need to be a square, or it can have basically pretty much any dimension, because your canvas can be of any size, right? And so can be your viewport. So now what I do is, let's say since I want to draw this landscape on this canvas, and now what I do is I start my painting with this top left cell, right? So what I do is I go to this top left cell and I come back to this net, and I look through this net to this landscape, and I try to figure out what is the color of the light that is reaching my eyes from this cell. So let's say this cell maps to this portion of the actual scenery, or the actual landscape. So I try to figure out what is the dominant color that I can see from this particular cell of the landscape, and I draw that particular color, or I paint that particular cell on the canvas using that color. So let's say the dominant color that I see from this cell is, let's say, green. So I paint this cell on my canvas as green. So I paint this as green. So let's say again, and I keep repeating this process. I go cell by cell across the viewport. So then, sorry, I go cell by cell across the canvas. So next I want to paint this cell of the canvas. So I again repeat the process. I come back to my viewport, or to my window of grids, and I look through this particular cell and try to figure out what is the dominant color that reaches my eye through this cell. Let's say this maps to this portion of the landscape, and I try to figure out what is the dominant color of this portion. Let's say it's red, so I try to, or let's say it's blue. So what I do is I paint this thing as blue, right? So this is how slowly we will have a mapping. We are trying to map this landscape onto this canvas using our viewport, using whatever color we are seeing through the particular cell. So every cell on this canvas is being mapped to a particular cell on the viewport, and the color reaching through our eye from that cell on the viewport determines what color the canvas will be painted at that particular cell. So this is pretty much how ray tracing is also going to work, right? So in a not so naive way, if I try to define this algorithm from a bird's eye view, what I am doing pretty much is I'm positioning this frame as required in front of my actual landscape, and I'm looking through the frame, and for each cell on the canvas, I'm pretty much finding out find out the mapped cell on our viewport. I'm calling this grid as our viewport, and then determine the color coming from that cell of that viewport, and we paint the cell on canvas with that color. So yep, it looks kind of simple, but it's not at all that simple, and we'll try to find out how we can determine what color reaches our eye from the particular grid on the viewport, right? This is the core of the ray tracing problem, where we try to determine which ray of light, so what is the dominant color of that ray of light that that's coming out from that particular cell is. And this is not at all simple, because a number of factors will determine the color of the ray coming out of that particular cell. What is the ambient light? So light is a whole separate domain that determines the color of the ray that's coming from an object and hitting our eye. So that's the next thing we will try to figure out, that is determining the color of the light that's reaching from that cell. Okay, so now that we have these basic components, that is our canvas, our viewport, and the scene, now let's map this to our 3D scene setup. So the first thing that we will now do is set up our 3D coordinate system and make certain assumptions regarding our world. So let's do that. So first let's get rid of this. So now let's set up our 3D coordinate system. Just like any other 3D coordinate system, we'll have 3 axes. So this is our y-axis, this is our x-axis, and this is our z-axis, right? So what we are assuming over here is that this is our origin. So let me quickly mark the origin. So this is the origin 0, 0, 0, and this origin is the location where our camera is placed. So camera is pretty much our eye, which is seeing the landscape. This is the one which is, the camera is the one which is receiving all the rays coming from our world. The convention that we want to follow is, this way is the positive y-axis, this is positive z-axis, and this is positive x-axis. So if we go this side, if we go this side, this is negative x. If we go down, it's negative y, and if we go this way, that will be negative z. Now remember, this is completely different from what the convention that's followed on digital screens, because on digital viewports or Cartesian planes, the origin is usually located at the top left corner, which I have mentioned in my previous videos. And so y increases downwards, and y decreases upwards, and x increases towards the right, which is fine. The actual difference is that the location of origin is changing over here. So in this case, the origin is at the center, which is not usually the case. Origin is usually at the top left corner, but we will make certain changes in the code to account for this, so when we draw the pixel on our image, we convert it to the digital screen system from this coordinate system, right? So now that we know our coordinate system, okay, let me get rid of these dotted lines. Okay, so we have our coordinate system, the part which is missing still is the viewport, that is our net with grids or our window with grids. So let's add that quickly. So just as in our physical world analogy, the net was placed just in front of our eye, even here the viewport will be placed just in front of the camera. Let's place the viewport somewhere over here. And again, the height and width of the viewport will be parallel to y and x axis. So this is our viewport. You can imagine that it has got grids, but I'm not drawing the grid right now. And so let's call the width of the viewport as VW, and let's call the height of the viewport as VH. So let's also assume that this viewport is placed at a distance of d from the origin. So this, let's consider this point as the center of the viewport as well, which aligns with the center of our coordinate system, that is the origin. And the other thing that I would do is, so that it's clear, what I'm going to do is I'm going to erase this part of this solid line. And I'm going to do a dotted line. Let's do a dotted line. Okay, so the origin perfectly coincides with the center of the viewport, and the viewport is placed as at a distance d from the origin. And now what we need to do is we need to choose values for VW, VH and D. So a standard value for VW, VH and D is 1. So if we assume that VW equal to VH equal to D equal to 1, that's kind of a standard value because it makes the viewing angle for the camera to be somewhere around approximately 53 degree, which is a very standard viewing angle. How it becomes 53 degree? Let's do a quick calculation. So this becomes a right angle triangle. Remember, this is the center point of the viewport. So if this becomes a right angle triangle, let's draw a triangle. And what we are trying to do is calculate this angle. So that is, if field of view is denoted by FOV equal to alpha, so this angle is half of alpha, right? So this is half of alpha, and what we are trying to calculate is pretty much this. So once we have half of alpha, alpha will just be the twice of that value. So this length pretty much here is half of VW, right? So what I'm trying to say is this is our triangle. I'm just changing the orientation of the triangle, and let's say this is our half of alpha, this is 90 degree. So the opposite of half of alpha is the height of this triangle, which is half of VW. Now VW is 1, so this is half, so this is half, and the base is pretty much d, so this is d and d is 1. So we know tan of half of alpha is basically half divided by 1, which is half. So half of alpha is tan inverse of half, and this value in degrees is somewhere around, if I quickly do tan inverse of half, that is pretty much math dot a tan 0.5. If I take the degrees, if I convert this into degrees, it's somewhere around 26.5. So it's approximately, and so it's approximately 26.5 degrees, and so alpha equal to 2 into 26.5, so it's alpha is roughly equal to 53 degree. That's how this entire this, if I draw another, so that if I just draw a dotted line, so that's how this entire entire angle is 53 degree, right? So now that we have established the viewport, our viewing angle, the other thing that we have to do is we need to find out a way to map the cells or the grid cells on our canvas to the cells on our viewport. So let's do that next. Okay, so let me again quickly remove all those things. Now the things that we know is VH equal to VW equal to D equal to 1, and our field of view equal to is almost equal to 53 degree, right? So these are the things that we have established or we have assumed. And now what we need to do is we need to somehow convert the canvas pixel coordinates to viewport pixel coordinates. So again, each cell on canvas is pretty much the pixel on our screen, like our pixel on our image. So what we are trying to do essentially here is convert the location or the coordinates of each pixel on the canvas or each pixel on a screen to their corresponding coordinates on the viewport, or rather their corresponding position or offset on the viewport. So let's do that. So let's assume our canvas, this is our canvas, this is our canvas, and its width is CW, height is CH, and we already have our viewport here, which is VW in width, VH in height. So along CW and CH, so first let's consider CW, right? First let's consider how we can map this width of the canvas to the width of the viewport. One unit of this canvas along CW will pretty much be VW by CW, right? Because that's like from unitary method, along the width, one width of CW will correspond to this value, VW divided by CW. That pretty much we are scaling. And then if we want to find out a particular Vx, that is the x coordinate of a particular cell on the viewport, that will pretty much be Vx equal to Cx into VW. So what we basically did over here is we found out what will be the Vx offset or the x offset on the viewport of a particular point whose x coordinate is Cx on the canvas, right? And we can do the same thing for Vy. So Vy equal to Cy into Vh by Ch. So what we found out over here is the y offset of a particular point on the viewport whose corresponding point's y coordinate is Cy on the canvas, right? That's what basically we did a mapping from the canvas to the viewport. So now we know for a point x comma y which positions ray we need to consider on the viewport. Okay, so now that we have established our viewport, assumed the viewing angle, as well as we know how to map our canvas pixels to viewport pixels or canvas cells to viewport cells, let's see how we can determine the color of the ray coming out from one cell of the viewport, right? That's the primary thing that we are after. So now what we'll do is we'll try to represent our camera. So let's say this is our tiny camera. Okay, and let's just consider another ray going to our camera, and it's meeting, let's say, somewhere over here, and this is a tiny cell of the viewport, and let's say it's intersecting on some object over here, and let us consider that's a tiny sphere. Let's say this is a sphere and its color is blue. So now what we have to do is we want to trace this ray that's coming from this object to our camera, and we want to determine what's the color of this ray. So this is the primary thing that we are after, the ray that's coming from this cell of the viewport to our camera. What the color of a particular object that reaches the camera is determined by a number of things. So it's determined by the base color of the object, right? For example, this object is of color blue, but not only that, there are several other factors like all the lights present in our scene. For example, there can be directional lights, the light rays coming from a very huge source of light, for example the sun, that can illuminate this object. There can be other sources of light like point lights. So point lights are the tiny sources of lights in the world, for example street lamps or bulbs or any tiny source of light that's present in the world. So the color of the ray coming from a point of an object to the camera is determined by the culmination, or is determined by the resultant light of all these light sources that fall on that particular point of the object, right? So what I'm trying to say in short is, the color of an object that we are perceiving or the camera is perceiving need not always be the true color of that object, but it can be the resultant color of the various light sources that's present in the scene that's impacting that object. But to keep things simple, we will simply consider that right now there is no light in the scene, and the color of the ray is determined only by the true color of the object, which is blue in this case. So in this case, the color of this cell will pretty much be blue. Now comes the other question: how do we trace this ray, or how do we mathematically express this ray that's coming from the object to the camera? So one thing we can do is we can try to simulate. So as I mentioned, there are number of light rays randomly going from one place to another in our scene, right? So let's say we have the sun, we have some street lights and all those things, and from all these light sources, because we can see something because of these light sources, because light from these sources hit the object, and then the fraction of those light rays which hit the object gets reflected towards the camera, right? So one thing that we can do is we can try to simulate all the light rays coming from these various light sources that are falling in the object, and then we can try to simulate a fraction of those light rays that get reflected from the object to the camera. But if we want to simulate all the light rays that is present in our environment, then it would be a freaking compute intensive task. Our rendering will be super slow, because we are trying to simulate a countably infinite number of rays, and it will be very slow and computationally intensive. So instead, what we are going to do is we are going to apply a neat trick where, instead of tracing a ray that is coming from the object to the camera, we are going to reverse trace a ray that has already come to the camera, that has already reached the camera from the object. So let's try to understand this from a bit lower level. The fact that we can see something from this given cell in the viewport means that some ray from the object in our scene has already traveled in that direction from that cell and has hit the camera, right? Let me repeat this thing. What I'm trying to say is the fact that we can see some color from that particular cell, or the fact that we can see something from that cell in the viewport already establishes the fact that there has to be at least one ray that has traveled from that object, or there has to be at least one ray from some light source in the scene that has got reflected from the object from a certain point on that object and has traveled along that particular cell of the viewport to the camera, right? And we are going to reverse trace that ray. So rather than forward trace, we are going to reverse trace this light ray that's reaching the camera, and we are going to find out the color of that light ray, right? So let's see how we can do that. So now we will take some help of vector algebra, and we will try to mathematically present our ray. So since we are reverse tracing, we will consider that the ray is going from the camera to the object rather than from object to camera. And so let's say the direction of the ray is towards this side, right? The ray is originating from the origin 0, 0, 0, and it's traveling towards this side. And let's say the point where this ray hits the viewport, that is this cell, this point is represented as V, right? This viewport cell is represented as V. So now how we can represent this ray? Even more important than how we can represent this ray is how we can represent any point that is lying on this ray. Let's say this point P lies on this ray, we can write the equation of this point P as P equal to this origin 0 plus a parameter T V minus O. So this is pretty much the parametric equation of this ray that we have written over here. So we took help of vector algebra and we are representing this ray that is originating at 0, 0, 0 and is hitting the viewport at V using its parametric form. So let's try to understand this a bit. So this is pretty much the direction of the ray. So V minus O is pretty much the direction of the ray. Why? Because the ray has originated at 0, 0, 0 and it is traveling towards V. So if origin is a point, V is a point, so the direction of the ray will be, since it's traveling from O to V, it will be V minus 0, V minus O, right? And T is a parameter using which we can move this point P along this ray. So let's say this is a ray and this is our ray direction. Now ray direction is pretty much D, let's say it is D, a vector which is V minus O, right? And let's say this point is origin, and now what we can do using this parametric form is, let's say we want to represent P, which is at a distance half of D from origin. So we can simply plug in T equal to 0.5, which will give us this point, which is 0 plus or O plus 0.5 D, right? So this is O and this is 0. So O plus 0.5 D, right? And if we plug in T equal to 1, then we will get this point, which is pretty much O plus D, right? So now we have the parametric equation of this ray. Now begins the fun part. We are going to determine the point of intersection where this ray hits the sphere. So for that, let's first get rid of all this thing and do some vector algebra once again. So let's say this is a sphere, right? And this is our ray, right? So this is our ray, which is originating at the origin, which is our camera, passing through V on our viewport and intersecting with a sphere, let's say. Now there can be multiple cases depending on how the ray is intersecting with the sphere. At most it can intersect at two places. One is here and another is here. So this can be one case where the ray completely passes through the sphere. Another case can be this, where it just touches the sphere. So basically the rays are tangent to the sphere at this point, right? So let's see how we can find out this point of intersection and how we can represent this mathematically. So what we are going to do is, let's say this is the center of the sphere, which is C, and for now let's say the point lies here, which is, let's say, P, the point of intersection, right? So this is our point of intersection, which also means this is the radius of the sphere, which is R, right? This is R. So we now have some basic assumptions. There is a ray which is intersecting with the sphere at a point P. The center of the sphere is at C and the radius of the sphere is R. So what we essentially know is distance P comma C equal to R, right? This much is clear. So one convention that I'll follow is the various points like C and P I will be denoting with capital letters, and when I am denoting a vector, I will use the usual vector notation. That is, for example, for a ray, I'll use the vector sign, the vector cap, right? So what we know now is distance P comma C equal to R, which I can say is that the length of this vector, so the length of the vector from C to P. So if I consider a vector from the point C to the point P, so that length of that vector CP is R, right? So I can expand this and I can say P minus C is R. So now what I can do is, if I take square on both sides, p minus c whole square equal to r square, right? Now this p minus c, like point p minus point c whole square, this I can also denote by p minus c. So p minus c is a vector dot p minus c, right? I'm just taking the dot product of p minus c with itself. So remember, the dot product of a vector with itself always gives us the square of its magnitude, right? So length is nothing but the magnitude of the vector. So this much is clear. That becomes p minus c whole square, or p minus c dot product p minus c equal to r square. And now the other equation we have with us is p equal to also 0 plus t d, right? Where d equal to, we know that d is nothing but v minus o. Okay, this much it's clear. Now if this is equation 1 and this is equation 2, we are going to plug in 2 in 1. So let's see how that looks. So I'm just going to reduce the font size a bit so that I can get more space. If we plug in p equal to o plus td in the first equation, what it turns out is o plus t d minus c dot product o plus t d minus c equal to r square. Now what we can do is, we can simply do once again vector dot product. We can apply the distributive law. Remember, we can perform dot product only between two vectors, and however we can also multiply a vector with constant. If we look at this o minus c factor, o minus c at both the places, so o minus c is nothing but the vector going from c to o, right? So we can simply reduce this to co plus, it's a vector, td dot co plus td equal to r square. Now what we can do is, we can apply the distributive law as I mentioned earlier. We can simply do co dot co plus td dot co plus, we need to multiply now once again td with co, so td dot co plus td dot td equal to r square. Now let's rearrange it a bit. What we have got is, now we have got a t square, so I'm considering this term t square in multiplied by dot product of d with itself, right? So now I'm considering this thing, so it will be t multiplied by 2 into 2 multiplied by d dot co plus, I have got co cross dot producted with co, which is co dot co equal to r square. Now what we have got essentially is a quadratic in t, because essentially these will all give us constants, because all, remember, dot product always gives you a scalar. Okay, so since now this is a quadratic in t, we can get two distinct values, or we can get the same solution, or we can get imaginary solution, right? Which kind of aligns with the actual physical situation here. The ray can intersect or touch the sphere at one point, or it can pass through the sphere, in which case it will touch the sphere in two places, or it can not touch the sphere at all, right? So we will have two solution, t1 comma t2. t1 comma t2 equal to, if I write the formula, y minus b plus minus root over b square minus 4ac divided by 2a, right? And let's see the terms over here. So our a is pretty much this one is a, which is d dot t. Our b is pretty much 2 into co into D. So finally our C, that is C of the quadratic formula, will be CO dot CO minus R squared. Why minus R squared? Because we are taking this R squared on the right hand side to the left hand side, so that the right hand side becomes 0, which is the usual quadratic form, right? So we have now all our A, B and C, and we can simply plug it into our quadratic formula and we can get our T1 and T2. Now among this T1 and T2, we will always choose the minimum of the two, because we always want the nearest T, that is the T which is nearest to the camera. Why so? Because let's say this ray, for example this ray, this is the camera, this is the camera, so this ray intersects here, T1 and T2. Now you can easily see that this T2 will be hidden behind T1, so we don't need to bother about T2 as of now, right? So at least in this version of ray tracer, where we are not considering transparent surfaces and things like that, we always need the nearest point of intersection, because the farthest one will always be hidden behind. So we will only focus on T1, this point. The color of the ray will be the true color of this surface. Okay, now let me draw a tiny boundary. Okay, so depending on the value of T that we get from solving this equation, solving this quadratic equation, we can divide our entire 3D space into 3 segments. So one value of T that we can get is less than 0, right? We can always get T to be less than 0. So this is the case when the point is, like the point of intersection with the sphere is behind the camera. So nothing says that the point of intersection cannot exist between the behind the camera, or we cannot have a surface behind the camera, right? But however, in this version of ray tracer, again, we will discard those cases. We will discard those points of intersection which occur behind the camera, and we will only consider the ones which are in front of the camera. So the other case can be 0 less than T less than equal to 1, right? So these are the cases where the point of intersection of the ray with the surface is located in the space between the camera and our viewport, right? So it's located in that space between these two. So it is point between camera and viewport, right? And finally, the most common case will be T greater than 1, which is point in front of viewport. So the point is basically located beyond our viewport, and that's why T is greater than 1. So these are the 3 segments. We will ignore T less than 0, and we will only consider the cases where T is greater than equal to 0. Okay, so next we'll see how we can convert all of these things into code. So we have all the basic things required for rendering a basic scene with just spheres. We have the vector representation of our ray, the parametric equation. We know how to calculate the intersection of ray with spheres, and we know which value of T to choose, right? So let's see how we can convert it into code and render our scene. Okay, so now let's write some code. So the first thing that we are going to do is update the screen draw pixel function. So remember, as I mentioned, that in this implementation, we are considering the origin to be at the center, but that's not the case for the computer graphics screen, because there the origin is located at the top left corner, which means in our implementation y increases upwards and decreases downwards, but in computer graphics screens y decreases upwards and increases downwards, so it simply inverts, and also the origin is translated. So let's do that. So whenever we will draw something on our image using raylib, we will translate our origin to the top left corner from the center. So for that, what we'll do is, let's create 2 variables, tx, which is translated x, is screen width divided by 2 plus x, and int t int sy is screen height divided by 2 minus y. The reason I'm doing minus y is because for y the direction changes. And finally, instead of plotting x comma y, we will plot tx and ty. Cool. Now, before moving further, we want to define some utility functions, and we will do those in the header file called easytracer.h. All these utility functions we'll be using in our main project. So the first thing that I want to define here is a struct to hold points on three-dimensional space. So any point on three-dimensional space has got three properties, right? The x, y, and z coordinates. For that, I'll create a struct here to hold the points in 3D space, and also every point in 3D space is a vector in itself. It's a point vector, that is a vector of that point relative to the origin. So that's why I will call it vec3, right? So let's quickly create the struct. So as I said, it will have three properties: x, y, and z, and we will call it vec3. Now we will create another struct to hold the parametric equation or the parametric form of a vector. So for that we will do, so remember, a parametric form has got three parts. One is the origin, from where the vector is originating, the direction, that is the direction of the vector, and a parameter called t, and the final form becomes o plus td. So we will store these three components in this struct. So first we will have vec3 origin, vec3 direction, and float t, and we will call it ray, because we will be representing rays in parametric form. And the next thing that I want to define is a type for our color. So our colors will also have primarily three properties, that is an R, G, and B. We do have a property for alpha, but I'll just consider that we have three primary properties, that is the color channels. So I will simply create a type def for that. So it will be based on vec3, and that's color3. And now some functions for addition and subtraction, negation of vectors. So first let's start with addition. So this will be used to add two vectors. So we will have vec3 star vec a. I'll be using pointers here. Vec b. So what I'll be returning is a new vector wherein the properties are the sum of the properties of the individual vectors. So vec a dot x plus vec p dot x comma vec a dot y plus vec b arrow y and vec a dot z plus vec b dot z. The next thing we are going to define is a function to negate a vector. Again, it will have only one parameter, and what we'll return is this. I'll create another function which will return a new vector from a given vector where each property will be squared. This will be pretty useful when we will be calculating things like the magnitude of the vector. So let's do that. Vector3 or vec3. So the next function that we'll create will simply return us the sum of the square of the individual properties or the individual components of the vector. So it will be useful while calculating the magnitude of a vector. It is simply the dot product of a vector with itself, right? So let's do that. So it will be pretty much, again, it won't be vec3, rather it will be float because it's a sum. So vec x into vec x plus vec y into vec y plus vec z into vec z. And using this, now we will create the magnitude function. So this function will calculate the magnitude or the length of the vector vec3 oops vec3 star vec. And what we would want is first the square of this vector, and on top of that we will do square root. Remember, it might seem a bit confusing, like the square root of a square would give us the same thing. This square is not a normal square, but it's the square of a vector. It's the sum of the square of the individual components of a vector, right? And of course square root is not present right now, so we will include the math class, the math header file, math.h, and that should fix it. Yep. Another very important utility function that we will be defining is constant multiplication, and let's do that. And float factor is the constant factor with which we will multiply this vector. So what we will return is another vector. Sorry, it won't be float, but rather it will be vec. Remember, multiplying a constant with a vector gives you a vector. So what we get is into factor comma vec a dot y into factor comma vec a dot z into factor. That was simple. Next we will define, sorry, not vec3 but float. We will define a function that will calculate the dot product between two vectors, and this will be an important one because we'll be using it a lot. So dot vec3 star vec a comma vec3 star vec p return vec a dot x into vec p dot x plus vec a dot y into vec p dot y plus vec a dot z into vec p dot z. The other one we will define is a function to calculate the cos of the angle between two vectors. Let's define that. Cos angle, float cos angle. Remember, the cos of an angle will always be a float. So we will have vec 3 star vec a and vec 3 star vec b. The cos of the angle between two vectors is nothing but the dot product between the two vectors divided by the multiplication of the magnitudes of the individual vectors, right? So it's pretty much like this. Let's say we have two vectors A and vector B, then cos, and let's say they make an angle alpha, then cos of the angle between them is pretty much the dot product of them divided by mod of A multiplied by the magnitude of B. So this is what we are trying to calculate here. So let's do that. Float dot vec A comma vec B, and that we divide with magnitude of vec A multiplied with magnitude of vec B. And one last function we will define is the function to subtract two vectors. So what it will do is it will subtract vec3 vec A and vec3 vec B. So what it will do is it will subtract vector B from vector A. So let's do that. And with our utility functions in place, this will be pretty easy. So we first will negate, so subtracting vector B from vector A is same as adding the negation of vector B to vector A, right? So let's do that. So first let's calculate the negation of vector B. That's negate vec B, and we will return addition of vec A comma, we will send the reference of negated vector. Cool. Now we have almost all our utility functions, and we will use, or we will include this file in our main.c. So let's do that. Cool. So next what we'll do is we'll create a function which will determine the direction of a ray originating from the origin. So remember, the direction of a ray originating from the origin is nothing but v minus o, right? So since the ray will pass from one of the cells in the viewport, let's say the cell is v and the origin is o, then the direction is simply v minus o. And this direction we will calculate corresponding to a pixel on our canvas. As we discussed, for every pixel or cell on the canvas, we are going to map that pixel or cell to a cell on the viewport, and then we will find the ray that passes from origin through that cell on that viewport, right? So let's say, so this function will call as screen to viewport, because actually we could name it something better, but as of now we will stick to this name. What it will essentially do is it will take a screen coordinate like a screen x comma y, right? So basically the coordinate of a pixel on the canvas, right? And it will find out the viewport cell corresponding to that pixel, and it will try to find the direction of the ray that is passing through that cell from origin, or basically origin is our camera, so the ray that passes from our camera through that viewport. So let's do that. Screen to viewport, not image but int sx. So sx and sy is the x and y coordinate of the canvas pixel or the canvas cell. And now we will apply that scaling formula. So what will essentially return is a vector or a three-dimensional point. Again, every point is a point vector. So what we are going to do is float so we are going to apply that formula, which is cx into viewport width divided by screen width. So we will just we are just using the term sx for cx over here. So let's do that. Sx into viewport. Okay, this reminds me we haven't defined the viewport width and height. So hash define viewport port width as 1.0 and hash define height as 1.0, and finally hash define camera view port distance as 1.0. Cool. So now hopefully it should Yeah, so now is x into viewport width divided by screen width, comma float sy into viewport height divided by screen height. And we are going to return this. So we pretty much did the same thing. So we first figured out vx and vy, right? And the vector will be, as mentioned, v minus o. So basically vx minus ox, vy minus oy, where o is the origin, and the z will simply be d, because that is the distance between camera and viewport, right? So that will be the z component, and we don't have to do minus ox and oy because both ox and oy are 0. So that's why it's simply this, and no subtraction is required. Next, what we are going to define is, remember, our scene is going to just contain some spheres. So we will define a struct to contain a sphere. So let's do that. Type def struct. So again, the sphere has got 3 components, right? The first component is the center of the sphere. The second component is obviously the radius of the sphere, and third is the color of the sphere, right? So let's do that. So vec3 center float radius and color 3 color, and we will call it sphere underscore, and let's define some more constants. We will have a vec3 origin. So our origin as of now is not changing, so let's create a constant for that, and this will simply be 0.0 dot 0.0 dot comma 0.0. Okay, and also define a background color. So when our ray doesn't hit any sphere or any object, it will return the background color. So let's do that. Okay, so now what I'm going to do is I'm going to go top down, right? I'm going to start with our main function and start with the entire ray tracing algorithm, and throughout the way I'll be defining certain function stubs or dummy functions which I'll populate later. So let me first define the function stubs, right? The functions that we'll be using in our entire ray tracing journey. So one of the core functions that we'll be using is the function called trace ray. This function will be responsible for tracing give a single ray coming out of the camera and going through our viewport into the world. So what it will finally return is a color, right? Because at the end of the day we are just interested with the final dominant color of the ray. So the first argument or the first parameter it will have is vec3 origin. I know origin is a constant right now. Origin is nothing but the location of the camera. I know it's constant right now, but I'll still treat it as a parameter as of now, so that in future if we want we can change the location of the camera to get a different perspective of our screen or our world. The second thing we want is, of course, the direction of the ray, right? And these I will be explaining in a moment. So what it actually is the lower and the upper bound on the value of the t, which is the solutions of our intersection between ray and spheres. So we will provide some boundaries between which we want our t to exist. Anything out of this boundary we will reject. So t max, we will have something called scene t. So this we have not defined yet, but this is nothing but our scene, and which is nothing but a collection of spheres, and we'll be defining it soon. So as of now I'll not define this function, but I'll just leave it like this. The other very important function that we'll be using is something called void get ray sphere intersection vec3. The parameters it will be taking is obviously the origin, again the ray direction of the given ray. A sphere with which it's trying to see whether the ray intersects or not, and the two values of t that we will be populating. So these are nothing but pointers to some variables which will get populated by this function, because obviously we can't return two values t1 and t2 from this function in C, so we will be using pointers, right? And again, I'll leave it as of now, I won't be populating it. Let's quickly define our scene type. So let's do so as of now our scene will simply contain array of spheres, that's why I'm doing sphere t star spheres, and I'll call it scene t. In future we'll have lights as well, but as of now it's just all spheres. Okay, now let's get rid of all these things and let's start with our main function top down. So first what I'm going to do is I'm going to define some spheres, that is an array of spheres. So let's put a sphere at 0, -1 and 3. Let's give it a radius of 1 and the color red. Okay, let's add another sphere. We will make it blue. Another. We'll make it green. And a final one, we will make it very large so that it acts as the ground. We will make it center very low so that, because its radius will be large, so that we can only see the top surface of the sphere. And we will give it a radius of 5000 and we'll make it yellow. Right, so that's our scene. I mean, that's our collection of spheres, and using that we will create a scene now. So scene t, scene dot spheres. We will malloc an array now, size of sphere t. Right, so now our scene has all these spheres, and now we will loop over all the pixels in our screen, that is our canvas, and we will try to trace rays corresponding to each and every pixel on the screen. So let's do that. So I'll have a x variable which will sweep from left to right of the screen. So -1 into, so remember our origin is at the center. I'll keep repeating this fact so that we don't get confused with the normal computer graphics screen where origin is on top left corner, and x less than equal to screen width by 2. So we start with negative screen width by 2 to positive screen width by 2. That should sweep, or that should cover the entire width of the screen or the canvas. X plus plus. And we'll do the same thing for the height as well. We will start from the bottom of the screen and we will go to the very top. So -1 into, or multiplied by screen width by 2 y less than equal to screen height by 2 y plus plus. Let's find the direction of the vector corresponding to this pixel on the canvas or the screen. So remember, what we necessarily will do now is find the viewport cell corresponding to this x comma y pixel on the screen, and we will get the direction of the ray originating from the camera going to our world through this particular cell v on the viewport. So let's do that. Vec3d, which is direction screen to, we'll use the screen to viewport function and we'll simply pass it x comma y. Okay, it will be vec3, and now we will have, and now we will use our trace ray function to determine the color of this ray. So for that, we'll first pass origin, then d. Then now for this, as of now, I'm going to consider all the t's, or all the intersection points that lie between, or that lie in front of our viewport. That is all the t's that's greater than 1 all the way up to infinity. So we will pass the lower bound of our t, that is t min, as 1, and the upper bound as infinity. Of course, we can't pass infinity, so we will pass something called t max. We will pass a reference to a scene as well. And of course, it's complaining that t max is not defined. So let's define t max. We will include something called limits, limits.h, and we will define t max as int max. So basically the maximum value for an integer. I mean, essentially we could have used any very large value, but yeah, this works. And finally what we will do is we will draw this color for this particular pixel. We will paint this pixel with this color on the canvas or our screen. So draw pixel x comma y comma color. Remember, color 3 is our definition of the color. We need to now typecast it to raylib's version of color. So we will do char color.x comma char color.z, so y color.z comma 255, right? And we'll finally pass a reference to our image as well. So that is the crux of our algorithm from a very top view, right? So next, what we are going to do is define our trace ray function. So now that we know how the ray tracing works, or reverse tracing works, defining the function will be pretty easy for us. First, let's assume that the closest t that we have found is t max, classic min finding algorithm, and then we will allocate a variable for the closest sphere t closest sphere. As of now it's null because we haven't found it. So basically what we are trying to find is that the sphere on which the closest t lies, right? So what we will do is, in this we will pretty much loop over all these spheres and we will see with which sphere our ray intersects, and we will get the closest sphere. We will loop over all the spheres. So there are 4 spheres. I am hard coding it. It doesn't look good, but as of now I am just hard coding 4. We can later make it a variable and convert it into a parameter, but as of now I'm keeping it simple. Then I'll just fetch the sphere at this index. I'll define 2 variables, t1 and t2, and I will call get sphere ray intersection. I'll pass origin, ray direction, the sphere, and reference to and basically pointers to T1 and T2 so that the intersection function can populate it. Now let's see if the T that we got is the closest T or the minimum T. So if T min is less than T1 and T1 is less than T max, so basically what we are checking is that this T is within our range. If that's the case and T1 is less than closest T, then what we'll simply do is we'll update our closest T with this T1 and we'll make closest sphere as the sphere at this index, right? And we will do the same thing for T2 as well. If T min less than T2 and T2 less than T max, if that's the case, we'll check again if it's the closest one, T2 less than closest T, then closest T equal to T2 and closest sphere equal to the sphere at this index. Okay, so now we have the closest sphere, and for some reason, if actually not some reason, in all those cases where the ray is not intersecting with any of the spheres, we will check if it's still null. If that's the case, we will simply return the background color. Otherwise, what we'll return is the color of the closest sphere dot color. Cool. And now let's quickly define the get ray sphere intersection function. Again, it's nothing but plugging in our ABC coefficients into the quadratic formula and solving for them and populating the T1 and T2 pointers. So let's store the radius in R. Remember, there was a factor called C minus O, that is which we were defining as CO. So let's do that. So here center is the center of the sphere, so let's define it as center to origin equal to subtract. Remember, CO means O minus C, so let's do that. Origin comma pointer to sphere dot center. Now let's define our coefficient. So A will be dot of ray. So let's see what is A once again. So A is d dot d. So ray direction dot the ray direction. So let's do that. D is 2 dot center to origin dot ray direction. So let's do that again. 2 multiplied by, again, dot product will give us a scalar, so we can do normal multiplication when we are multiplying it with 2. So dot and center to origin comma ray dir, and finally float C equal to, once again, dot, let's see what was that, CO dot CO minus R squared. So center to origin comma center to origin minus R into R multiplied by R. That's it. And now let's find the discriminant. Discriminant. Yeah, discriminant. B squared minus 4AC. The classic discriminant formula. If discriminant is less than 0, we don't have any real solution, so we will simply populate T1 and T2 with T max, that is no solution at all. T max And finally we will calculate the two solutions. Sorry, float of the first factor is -1 into b plus sqrt discriminant, and we divide this entire thing by 2 into a into 1.0 just to make sure it's float. And we have got a t2, which is pretty much the same thing, right? It's the same thing, so I'll just copy paste it, make it t2, and instead of plus it will be minus. So minus b plus minus b squared minus 4ac root over, and we will return. That's our full ray tracing algorithm in how much? 100, let's say 115 lines of code. I mean, keeping aside the utility functions, which anyways we couldn't have avoided, it's just 115 lines of code. Okay, let's try to compile it now. As usual, there are some errors. Let's try to fix them. There's an error on line 61. Okay. And we have our image, and it's exactly what we had decided to generate, 3 spheres. So we have got our green sphere, we have got our blue sphere, the red sphere, and the yellow sphere is so big that it appears to be a flat surface. So that's the tiny version of our basic ray tracer with no lighting, shading at all. It just displays 3 spheres. I know the image doesn't look that interesting, but this simple image shows us how the ray tracing algorithm works at its core, keeping aside lighting and shading, how the basic algorithm works, its internals, and how we can use it to generate this image from scratch. In next videos, we will try to understand how we can use lighting, how lighting affects the color of a surface, and how it affects the color of the rays that is bouncing back from the surface to the camera. We will consider different sources of light like directional lights, point source of lights, and things like that. We will talk about different types of surfaces or materials like matte objects which disperse light. We will talk about shiny objects. We will talk about transparent and reflective surfaces. We'll talk about all those kind of things in the upcoming videos. So yeah, that's it for this video, and hope you all liked it, and see you all in the next video.